Hello, welcome back to the NPTEL online certification course on deep learning. For our previous classes, we have talked about various deep neural network architectures. We have also talked about the algorithms for training the neural networks, and we have also talked about the algorithms of how to make or how to train the neural network more efficiently, or how to make the learning process faster as well as more accurate. Now, given this background of the architecture of deep neural networks and the training of deep neural networks, now it is time to look at some of the use cases or where the neural networks or deep neural networks, particularly the convolutional neural networks, have been used in real life practice. So, today we will talk about one of the applications which has been published in one of the literature, that is the application of face recognition or face verification, the network known as FaceNet. After discussing about FaceNet, we will talk about other applications of the neural networks, say for example, use of neural network for segmentation purpose, because so far what we have seen is the neural networks which are being used for the recognition purpose or classification purpose. That is how we have seen that the neural networks are being trained. Now, the classification problem where entire image is classified belonging to different classes, say for example, image of a dog or image of a bird. The segmentation problem is something like classifying every pixel within the image to belong to different classes. And when you collect all those pixels belonging to a particular class, that becomes a segment. So, moving from image level classification to pixel level classification, we will talk about after today's discussion, and we will see that what are the architectural as well as algorithmic modifications that you need in those deep neural network architectures, so that you can take decisions not only at the image level, but you can take decisions at a finer, that is at the pixel level. So, we will talk about that in our future lectures. So, today we will talk about a face recognition system. We will see that how the face recognition system is important in today's digital world. Then we will talk about a learning mechanism which is known as one-shot learning, which is very applicable in face recognition systems. Then a particular network which employs face recognition is FaceNet. We will discuss about that. And for training of FaceNet, the corresponding loss function which is known as triplet loss. We will discuss about this triplet loss, and we will also talk about how to select the proper triplets for training of the FaceNet. Right. So, let us see that what is the importance of a face recognition system. In today's world, face recognition has become very important. Say for example, think of a situation that you are going to an ATM for withdrawing your money from your own bank account. So, currently what we do is, while withdrawing the money, we swipe our ATM card, then we are prompted to enter the PIN, which is a secret code that only the owner of the account should know. But won't it be better to improve upon the security, so that in the ATM system, suppose or in the tailoring machine, we have camera that will take image of your face when you stand in front of the ATM machine, and then your face image will be matched with the image which is already there in the database of the bank. So, this is a sort of authentication or security that you are withdrawing money from your own account through the ATM in absence of any persons from the bank being present over there. So, right now there are two different modalities which are mostly used. One is authentication based on the fingerprint. In addition to that, the authentication based on face recognition can also be employed. Think of another application, that is access and security. So there are many areas or many offices which are highly secured. That is, only the authorized persons are allowed to enter those offices, because there may be some strictly confidential documents or strictly confidential information that might be available in that machine, in that particular office. So those offices are not accessible to any person. Only the authorized person can access those offices, and if we want to automate this particular process. So before you have an access to the office, there might be a camera taking your face image, and then try to verify with an image which is already available in the database, that whether your face image is same as the image of an authorized person, which is already authorized by the authority. And only when it is authenticated, that is, yes, it is the same person, then only you are given entry to that particular office. So this is another application of face recognition or face based authentication, commonly known as biometric authentication. Similarly, criminal identification, particularly criminal identification from fraud. In many cases, if you visit a police station, you will find that photographs of wanted persons are pasted on the notice board. In some cases, it is also written that most wanted. So if there is any notorious criminal who is being whom the police is trying to find out, and the fellow is hiding somewhere. So can we identify that person if the person moves along with a mob in a mob, right? So you take the face images from the mob and try to identify whether that person is present within the mob or not. Similarly, there are many such applications. The applications of face recognition or face authentication can be in advertising industry, it can be in healthcare applications, and the applications are many more. So you find that face recognition has become a very, very important aspect in today's digital world. However, though it is very, very important, the face recognition task is not very simple. In fact, there are many challenges. So some of the challenges are as given in these photographs. You find that all these face images are photographs of the same person. Of course, these photographs are taken from this particular paper, which is cited at the bottom. You find that though these face images are for the same person, but it is very difficult to identify or very difficult to match that they are face images of the same person. The reason being, when the images are captured, the illumination conditions may be different. So the images might have been captured under different illumination conditions. Maybe the person was in different pose, or the face was in different orientation. In addition to that, the face may be in different scale as well, not only orientation and pose, even the scale or the magnification may be different. There may be various such other variational conditions which makes the images of the same person or the face images of the same person to appear to be different. So these are the challenges to make your face recognition system work, or even to design a face recognition system. And of course, one of the most important challenges, the availability of a limited data set for training of the system, so that the system can identify, the system can recognize face persons from their face images with high accuracy. So these are the different challenges. So given this, the kind of training mechanism or the learning mechanism that has to be employed is what is known as one-shot learning or one-shot training. So what is this one-shot learning? This one-shot learning is a very, it's a problem or categorization problem which is found mostly in computer vision applications. As we have seen before, that while training of deep neural networks or training of machine learning algorithms, that the deep learning algorithms are data hungry. That means you need millions and millions of data for training of the neural network. But that may not be true when we think of designing a face authentication system or a face recognition system. So Oneshot learning actually tries to learn or tries to learn the face images or learn about the object categories from one or maybe very few training samples which are available. Now, why the samples are very few? What's the problem in getting large number of images that we use in other machine learning algorithms? You think of a situation that a face recognition system or face-based authentication system which is used by a very small organization for security purpose, and that particular organization has a small number of employees working in that particular organization. So what the organization may try to do is, at the beginning when a person joins that organization, it may try to take, which you all have faced, that when you apply for something, the organization asks for your passport photograph, right? When you apply for whether for admission or opening a bank account or applying for some examination or something, apply for identity card, you are asked to provide your passport size photograph. So here again, in the same manner, when an employee joins that organization, the organization may take a very nice photograph for that person. So you find that as the organization is small, the number of such photographs which will be used for training purpose, of course, is very, very small, not many photographs of a particular person. So the network or the authentication system, the recognition system, has to be trained using only those few photographs, right? Or maybe some more photographs that can be taken at random. So using that, it is expected that the system will be able to identify persons who are employees of that organization, who will have maybe free access to all different facilities of that organization, or it will also be able to identify the persons who are not employees of that organization but maybe customers or even in some cases service providers. So there are different categories of people may be visiting that particular office, and the face-based authentication system should be able to identify whether the person is an employee or the person is a customer or the person is a service provider or which category he is. And here you find that because the number of images that you have are very few for training the network or the authentication system, so the normal machine learning algorithms cannot be applied in this case. Rather, this particular problem of learning becomes a one-shot, or maybe we can call it a few-shot learning problem, where the learning has to be done using very few images which are available. So what does this FaceNet actually do, or the FaceNet, the face recognition system? The FaceNet actually learns an embedding function, the fx, where x is an input image or an input face image. So from this face image, this FaceNet learns an embedding function fx with the constant that mod of fx should be equal to 1. That is for normalization purpose. Or in other words, we can write that the FaceNet learns a function f which maps your input face image x. Of course, here we assume that this input face image x is of size m by n. So m by n number of pixels. So it learns a mapping or learns an embedding of an input face image x to a d-dimensional feature vector. So it maps x, which belongs to r m by n, to r d. And if d is less than m by n, then what we are gaining is an image of size m by n is being represented or is being embedded which is known as embedding, it is being embedded into a d-dimensional space. So you remember that in our earlier discussions of this particular course, we have talked about the feature vectors. That is, we said that given an image, if I can represent that image by a feature vector of dimension d, then basically what we are doing is we are mapping that image or transforming that image into a vector in a d-dimensional space. And exactly that is what is being done here. So in traditional machine learning applications, that d-dimensional vector has to be decided that what will be the components of those d-dimensional vectors. Some component may represent intensity, some component may represent color, some component may represent the texture, some component may represent shape of that particular region, and so on. So it has to be handcrafted. And the advantage, we said, that moment I transform an image into a vector in a d-dimensional vector, that means I am representing that image by a point in a d-dimensional space. And exactly the same thing is done over here, but here this embedding function, which is f, that embeds an input image to a d-dimensional vector, or it represents that input image, embeds this input image to a d-dimensional space as a vector. This is not handcrafted, but the machine or the deep neural network has to learn this embedding function f by making use of the training data which is made available to the system. And the approach is, again, as we have seen before, that we have to define a loss function, and the gradient descent on that loss function in a backpropagation way will train the neural network in such a way that this deep neural network will learn this embedding function f. Right. So the advantage that we said, even we have said earlier, that if I take two images, say xi and xj, so xi is an image, xj is an image, both of them are embedded in that d-dimensional space, maybe an Euclidean space, through this embedding function f. So f of xi is the embedding of image xi, and f of xj is the embedding of image xj. So xi minus xj mod of that square, this indicates the squared Euclidean distance between these two embeddings fxi and fxj. Now, if xi and xj, these two images are images of the same person, maybe in different orientation, maybe in different pose, maybe under different illumination, whatever. But what is expected is, if xi and xj are the images of the same person, then the distance between fxi and fxj should be very small. Or in other words, mod of fxi minus fxj square, which is actually the squared Euclidean distance between fxi and fxj, that should be small if xi and xj are images of the same person. But if xi and xj are images of different persons, then what we want is that this squared Euclidean distance between fxi and fxj should be large. And that is how you measure the similarity, whether the two images are similar or not. So given this, now this FaceNet, the architecture is something like this. It has an input batch layer where you feed in the training data or even the inference data, the test data. The FaceNet is actually a deep convolution neural network architecture, which is a deep neural network. And then I have an L2 normalization layer, because you find that we had put a constant that this embedding function fx should be such, or embedding should be such, that mod of fx should be equal to 1, and that is what is achieved through this L2 normalization layer L2. And after this, what we get is the embedding of your input image x. So this is where I get f of x. So this FaceNet, it uses a deep convolutional neural network model to learn the embedding function fx, and it consists of an input batch layer and followed by a deep convolution layer, which is followed by an L2 normalization layer or normalization operation, and finally we get an embedding of the input image into a d-dimensional Euclidean space. So here basically what I am getting is a d-dimensional vector, the vector which is embedding of your input image. So this is how the FaceNet works. And once your embedded vector or the embedding is complete, then your decision is taken in this embedding domain only, that is in the d-dimensional space. I don't have to take decision in the original image space where the images are of size m by n. So this work, which we are going to discuss today, was presented in this particular paper, FaceNet, a unified embedding for the face recognition and clustering, as has been given over here. So let us see how this network actually works. So the first and foremost thing is, of course, we have to train this network, and for training of this network, what we need is we have to define a loss function, and that training has to be done by an gradient descent approach, where gradient descent algorithm will try to minimize the loss function. So the loss function, which is defined in this FaceNet, is what is known as a triplet loss, and that is used for the training purpose. So the triplet loss, when you define a triplet loss function, the triplet loss function actually makes use of three images. One is anchor image. So what you said is the particular example that I have taken for a small organization where we can have passport size photographs. We can ask the employees to give their passport size photographs, right? And those images can act as anchor images. And then I need two more images. One of the, and so those are anchor images, say A. So I call them as anchor images A, right? And I need two more images, that is another image of the same person, but which is different from the anchor image, and we call them as image P, or this is a positive image, as this is image of the same person. And I need image of another person, not the same person, which we call as negative image N. Then once I have this, then if I compute the distance between FA and FP, that is FA is the embedding of the anchor image A, FP is the embedding of the positive image P, that is A and P are from the same person, and Fn is the embedding of the negative image, that is image of not the same person as that of the, and it is not of the same person. So that is what is my negative image. So what you do is you compute the distance between Fa and Fp, which is dFa dFa-Fp, and you compute the distance between Fa and Fn, that is the distance between the anchor image and the positive image, and the distance between the anchor image and the negative image. So obviously in this case what is desired is that the distance between anchor image and the positive image should be less than the distance between the anchor image and the negative image, right? Or in other words, what we desire is that mod of Fxa, Xa is the anchor image, minus Fxp square, that is the squared Euclidean distance, must be less than f of Xa minus f of Xn square, right? And that is quite obvious, because Xa and Xp are for the same person, Xa and Xn, they are for different persons. Now the problem is the model can learn to make the same encoding for different images belonging to the same person, and if it is so, then Fxa minus Fxp because it is the same embedding, so that will be equal to 0. And if it is 0, then the first condition which is desired, that is f of xa minus f of xp squared less than f of xa minus f of xn squared, that will be true always. And if it is always true, that means there will be no further learning, as there will be no triplet loss function. Triplet loss will always be 0. So the model stops learning. The solution to this is by putting a margin, say alpha. So what this alpha does is it maintains a gap between a and p and a and n. So what we have, a triplet loss function must be something like this, that f of xa minus f of xp squared plus alpha must be less than f of xa minus f of xn squared, right? So diagrammatically I can put it this way, that this is my anchor, this is my positive sample, the distance between these two is this, and the distance between anchor and negative sample is this, okay? And this is what is my margin, that is what is alpha, right? So I want that the distance between these two must differ at least by alpha, and that leads to a loss function which is given by this, that L equal to fxa minus fxp squared minus fxa minus fxn squared plus alpha, take the summation over all possible triplets. Triplets are xa, xp and xn, and you try to minimize this loss while training of your neural network or the FaceNet. So this is what this is how the FaceNet is trained. So once the FaceNet is trained, actually what this FaceNet tries to do is it tries to make, because I want that the distance of the anchor from the positive sample should be low and the distance of the anchor from the negative sample should be high. So FaceNet actually tries to make compact clusters of the images belonging to the same person, whereas the clusters of the images belonging to different persons should be wide apart. That is what is being tried by the FaceNet. So images belonging to the same person forms a compact cluster. So every pair of images within the same cluster, the distance between every such pair should be very, very small. So this is how triplet loss is used for training of the FaceNet. Now the problem that becomes is that how to select this triplet, because if we have a database of large number of images, selecting of all possible triplets becomes very, very difficult. I mean, it is extremely time consuming. So what you try to do is you form the mini batches and you select the triplets within the mini batches, so your computation time will be low, because selection of the triplets is very, very important. And there what we have to do is we have to try to find out the hard positive triplets and the hard negative triplets. That means we should try to find out the pair of hard positive triplets, or a positive triplet whose distance from the anchor is very large, and I have to find out a negative triplet whose distance from the anchor is small, okay? And these are the pairs which actually gives you faster learning of this network. So selection of the triplet is also very, very important. So in many cases what you do is, instead of trying to find out the hardest negative sample, you try to find out a semi-hard negative sample that just satisfies that distance between the anchor and the positive sample is just less than the distance between the anchor and the negative sample, and you forget about the margin that we discussed about earlier. So while training, I can try to look for a negative sample which may be within this margin. So these are the samples which are actually semi-hard negative samples. It may not be hard negative samples, okay, because selection of those may be easier. So once you have all this and your network is trained, then for given any input image, output becomes a vector, which is an embedding of your input image to a d-dimensional space. And then your recognition or verification can be done in that space only. Say for example, the verification is given an image or given two images, I have to say whether the two images belong to the same person or not. So what you do is you give the image, pass the image to the same network, and you get the embeddings of the two images. If the distance between the two embeddings is less than certain threshold value, I can always say that they belong to the same person. And if one of them is actually an anchor image, I can verify that the other image is image of that person only. Similarly, in case of recognition, I can make use of KNN classifier. Given an image, you get its embedding, find out, you select k number of embedding which are the nearest to it, and then you go for a voting mechanism. So within this k number of embedding, whichever is in majority, you recognize this image to be the image of that person which is in majority. So that becomes your classification or recognition problem. And in the same manner, we can also find out that or we can also cluster face images in that embedding space. That is, all the embedded vectors which are very close to each other, they form one cluster, and which are not close, they become part of different clusters. So this is how the FaceNet actually works, and as we have seen that FaceNet has or face recognition or face verification techniques has wide applications in today's digital world. So we stop face recognition today. In our next class, in our next lectures, we will talk about other applications of the deep neural network. Thank you.